So we're going to talk about heat now, and specifically the difference between heat and energy. So first, what happens when you touch a piece of ice? Well, of course, it feels cold, but the idea is what happens in terms of energy whenever you touch the ice. So before I mentioned that there is no such thing as cold, that it's just an absence of heat or it's a removal of heat. And so what happens when you touch a piece of ice is the ice removes energy from your hand. So you lose energy, the ice gains the energy, and that was a transfer of heat. That's why it feels cold. Now, what happens if you touch a hot burner on the stove? Well, of course, you know your hand burns. And the reason why is because the burner is hotter than your hand is, which means it has more temperature or more average kinetic energy than your hand. So your hand pulls energy from the burner, thereby increasing the temperature of your hand and causing a burn. So what is heat? This is your definition of heat. So if you want to make sure to star this, that would be great. Heat is energy that flows from a difference in temperature. Okay, so it flows from difference in temperature, which means a substance does not create or does not contain heat. Instead, it contains energy. Please make sure you emphasize these in some way in your notes, where you star them, you underline them, you highlight something. But a substance contains energy, not heat. Heat is the flow of energy. So in the examples up here, heat is the flow of energy from your hand to the ice or from the burner to your hand. But the energy was contained in the objects, and that energy moves as heat. So heat transfer. Objects receiving heat have an increased level of kinetic energy. So that makes sense. If an object is gaining energy, then of course it's going to have more kinetic energy. So it has an increase in internal kinetic energy, and we always flow from high temperature to low temperature. So in the examples with the ice in your hand has a higher temperature, so the energy will flow from your hand to the ice. With the burner, it flows from the burner to your hand. Now, heat does not necessarily flow from objects of greater total energy to objects of lesser total energy. And so why would that be? So think about your definition of temperature. So I would write this answer down to make sure you got it. The reason why is because we're looking at the energy per particle. So not the total, but the per particle. So my favorite example for this one is a cup of cocoa. So if you've got a cup of cocoa in a cold room, which one has a greater temperature? Well, of course the cocoa does, right? The cocoa is hot, whereas the temperature in the room is cold. Now, which one would have a greater total energy? Well, since the room is so massive, then the room would have a greater total energy, whereas the cup would have a smaller total energy. But each particle in the cocoa has more energy than in the room, so the cup will give the energy to the room. So it's not total energy, it's the average energy. So it's the amount of energy per particle. So the energy will always flow from the hot cocoa to the cold room. And heat will continue to flow until equilibrium is reached. So in the cocoa example, if you left that cup of cocoa out, eventually that cup of cocoa would get to room temperature. And so now the cocoa and the room would be the same temperature, and that's when you reach equilibrium, equal temperatures. So we're going to go through the three different methods of heat transfer: conduction, convection, and radiation. So the first one is conduction, and make sure you underline this or highlight or something, but it's energy transfer from particle to particle, which means it requires direct contact. Okay, direct contact. So in our picture here, conduction is whenever this end of this rod gets hot, then particle by particle in the rod, the energy is moved down the rod. Hence, you have to hold it with a glove. Here in the example with the stovetop, the eye gets hot. The pot is in direct contact with the eye. So in direct contact, it transfers heat to the pot. The pot is in direct contact with the water, so it transfers through conduction to the water. This is what we talk about in terms of conductors and insulators most directly, is with conduction. So pots are made out of metal or other very good conducting materials so that the energy goes from the stovetop to what's inside the pot very easily. So direct contact. Convection. Convection is heat transfer through motion of a fluid. And here fluid just means something that flows. So it can be solid, liquid, or gas. So examples here, hot fluids rise because they are less dense than surrounding cooler fluid. So here in this picture, we have warm air from the surface rising up into the atmosphere. So here air is the fluid. So we have warm air rising. In our picture before, here you see the air right above the fire is warming, and that is rising because of it being less dense. Examples, hot air balloons. The way they work, you heat the air in the balloon, which causes that warm air to rise, and then the balloon goes up. The balloons do not have any kind of special gas in them, it's just air. Weather. This is how we get storms and rain and things like that, is that warm air from the ground rises up and forms these clouds once it starts cooling again as it's rising. Heating a house. If you have a two-story house, you've probably noticed that your upper floor is usually warmer than your lower floor, and that's because, again, warm air rises. So most of your heating will go up, and so the upper floor will be hotter than the lower floor. Here's a video demonstrating this idea. So here, this woman is putting some green food coloring in at the top, and what you notice right now is it's evenly distributed, so it's diffusing evenly. But now she's heating one side of this glass tube. It's causing the water here to heat up and causing it to rise. And in the process, it is now pushing the green food coloring through the loop. And now you see it's not going this way anymore. Instead, all the food coloring is being pushed in this direction because the water here is heating and rising. So the last kind is radiation, and radiation is energy transmitted by electromagnetic wave. So this is what you would want to star or highlight or underline, because this is your definition for radiation, transmitted by electromagnetic wave. So what this means is you get energy from the sun or energy from a lamp. Whenever you have your hand or whenever you're standing next to a light bulb and you can feel the heat from it, it's because you feel that heat radiating from the light bulb. Same with the sun. The reason why the sun feels so warm whenever you're standing outside during the day is because you're feeling that heat by radiation from the sun. What's nice is that radiation does not require a medium, which means it can travel through a vacuum. So it can travel through space. This is a great thing because if radiation couldn't travel through a vacuum, then we wouldn't get any sunlight. We wouldn't get any energy from the sun, and we would be extremely, extremely cold. So I'm very thankful that radiation can travel through a vacuum. Radiation is pure energy. So these electromagnetic waves, which we'll get to waves later, but the idea is these waves are pure energy. So there's no particles or anything involved. It is just pure energy that is traveling. And that energy is then gained by objects. So in this example here, the energy from the sun is gained by the ground in the greenhouse, and it increases the kinetic energy of the object that it then hits. So This becomes warmer because it's gaining energy from those rays, which then increases the kinetic energy, increasing temperature. So radiation by electromagnetic wave can travel through a vacuum. So one type of radiation is called infrared, and you've probably heard of like infrared cameras, infrared goggles, things like that. This is a type of radiation. It's heat. Basically, it's called heat waves. And so here we have a picture in daylight versus nighttime. And what you should notice here is how bright the ground is. So it's very white. And that's because the sunlight is hitting it, and the ground is now radiating that heat as infrared back up. The reason why it's very dark here is because that's the shadow. It's the shadow of our tree that is right here. So this tree is radiating some heat itself, but then because of the shadow, this area is not gaining that energy from the sun, and so it's not radiating as much. Now at night, since it's no longer getting that energy source from the sun, the ground still radiates some heat, just not as much. So here, gaining lots of kinetic energy from the sun, here, just releasing that extra that it had. So the last thing in terms of gaining and losing heat comes from Newton's law of cooling. So the idea is the rate of heat exchange is directly proportional to the temperature difference. Now this term is usually really hard for students to understand, so let's see if I can help with the cup of cocoa. You have a hot cup of cocoa in a very warm room versus a cup of cocoa, hot cup of cocoa, in a very cold room. The warm room will keep the cup of cocoa warmer longer because the difference between the room and the cocoa is smaller. Smaller temperature difference, smaller rate of heat exchange, so smaller release of energy. In the cold room, there's a larger temperature difference between the room and the cup, so there's a larger rate of heat exchange or larger release of energy. So this is why whenever it's really cold outside, your house will lose heat very quickly versus whenever it's just kind of cold outside. So your heat will always run much more. Your heating systems will run a whole lot more whenever it's very cold outside because your house is losing more heat more quickly because of this law of cooling. This is also why frozen food will thaw quicker on a counter than in the fridge, because the counter versus the food is a larger temperature difference than the frozen food in the fridge. Now, why is this bad? Well, you don't want the outside thawing faster than the inside of your frozen food, especially if it's meat, because then it goes bad and it has bacteria and you get sick and it's no fun. So if you're trying to defrost something, you either want to put it in the fridge or put it in a water bath, because water kind of insulates that cold. It keeps it from defrosting too quickly. Now this also works for heating, so the larger the temperature difference, the faster something will heat up as well.